So hopefully you've had a chance to look at the in-class activities and internalize some of the lemmas that are going to be necessary for proving the extreme value theorem. We're going to go ahead and put those together and actually finish off the proof. So we're going to review one of the lemmas from the in-class activities. That's going to be very helpful. We're going to outline the two main problems that we must solve. We talked about it in the last video, and you hopefully thought about it and encountered it when you were working on the in-class activities as well. We're going to solve each of those two problems, and then we're going to put the reasoning together in both of those for the proof of the main theorem. So here it turns out was a very, I want to say simple, maybe not easy, but simple lemma that is extremely useful in this theorem. So if you have a set B of real numbers, if B is bounded above, then you can find a sequence in B that converges to the supremum. And if it's bounded below, then you can find a sequence that converges to the infimum. And the proof, I mean, once you see the proof, it's like, oh yeah, of course that's what it is. But getting there might be a little bit tricky. So basically what we're looking is at a sequence of numbers for the first one. So we're looking at the bounded above one. So we're looking at the supremum minus 1 over n. And that is a sequence. That is a sequence of numbers. I didn't put the little curly brackets around them, but you get a number for each n. And a couple things happening with those numbers. First of all, they're smaller than s. And second of all, they're getting closer and closer to s as n gets really big. So since s is a supremum, and s minus 1 over n is smaller than s minus 1 over n is not an upper bound of b. That means for each of those s minus 1 over n's, there is some number in b, we'll call it xn, such that xn is greater than s minus 1 over n. And our claim is that the sequence xn converges to s, and that turns out to be super easy once you try to use the squeeze theorem, right? Because we know that xn is less than or equal to s. After all, s is an upper bound for b. We know xn is greater than s minus 1 over n. That's how we defined xn. And the sequences s minus 1 over n and just the constant sequence s both converge to s. By the squeeze theorem, xn also converges to s, and that completes the proof. The one about infimum is very similar. Instead of looking at s minus 1 over n as we did for the supremum, you're going to look at, let me see, t is the infimum. You're going to look at t plus 1 over n. And again, sort of get a mirror image proof to 1. All right, so let's look now at trying to get the main theorem. Remember, our hypothesis was that f is a function from the closed interval ab, it's very important that it's closed actually, to the real numbers. Let that be a continuous function. And then I want to look at the range of f. And there's a couple of things that can be wrong with the range of f to make it so that f doesn't have a maximum or a minimum, or maybe or both. But we found two issues that we had to resolve. Again, either from the last video or through working those problems in the activities. We need to prove that R is bounded. If it's not bounded, then the elements can get arbitrarily large, which means you can't have a maximum or minimum, or large or negative, right? If it is bounded, and if the range has an infimum s and a supremum t, it might not be the case that either of those is actually in the range. So we need to actually prove that the infimum and supremum of R are in the range. So we're going to prove those in two separate steps. We don't have to do them all at once. So the first one is let f be a function from the closed interval ab to the real numbers. Let that be a continuous function. Then the range is bounded. So we're going to prove this by contradiction, which means we're going to assume that the range is not bounded above. We have to consider the case where it's not bounded below as well, but as we will see, it's going to be very similar. Then for each natural number n, there exists some real number in R, something in the range that is at least as big as n. If that were not the case, then n would be an upper bound for the range, but we're assuming that it doesn't have an upper bound, right? So every natural number, there's something in the range that's bigger than it, maybe a lot of things, I don't know, but we're just choosing one of those to be our Rn. So we know Rn is in the range. That means it is the output of the function. That means there's some input, we'll call it xn, such that f of xn is equal to Rn. And so plugging that in for Rn into our inequality says that f of xn is greater than or equal to n for each n. That means the sequence f of xn is an unbounded sequence. Now things are going to get interesting. And note that that also means that every subsequence is going to be unbounded, right? If we had a subsequence that was bounded, then yes, we would have some issues. So every subsequence of f of n, xn is going to be unbounded as well. And therefore it's divergent. So note that each xn is in the closed interval ab, and that means that xn is a bounded sequence. So the inputs form a bounded sequence, the outputs form an unbounded sequence. So by Bolzano-Weierstrass, what do we have? There's going to be a subsequence xpn that converges to some limit L. That's true for every bounded sequence. Furthermore, since f is continuous, that implies that f of xpn is going to converge to f of L, right? That was our link between continuous functions, between limits, and between sequences. But we already concluded in the last slide that f of xpn is divergent. So it can't be both divergent and converging to f of L. So that's a contradiction. And the case where r is not bounded below follows similarly. We again make a sequence of elements in the range that are below negative n, right? So negative n goes to negative infinity because it's not bounded below. We can choose an r that is less than or equal to negative n. The rest of the proof goes the same way. So now we're ready to prove our extreme value theorem. All we have to do is figure out that second issue, right? Let f be a function from the closed interval ab to the real numbers, let that be a continuous function. Then f has both a maximum and a minimum value. In other words, there are two inputs, c and d, such that every output is greater than or equal to f of c and less than or equal to f of d. All right, so we already proved that the range of f is going to be bounded. That means the range has both a supremum and an infimum. Then all we need to do is prove that that supremum and infimum are in the range themselves. So let's go do it. So we're going to let S be the infimum, let T be the supremum, so we don't have to keep writing inf and sup all the time. So remember the lemma at the beginning of the video. We know that there exist two sequences actually. One Sn that converges to the infimum S, and then Tn converges to the supremum T, right? That is true for any set that's bounded below or bounded above, right? There's always a sequence that converges to the infimum. There's always another sequence that converges to the supremum in the set. So we know that Sn and Tn are in R. That means they have some inputs that give them as outputs. That means you have, we'll call them Cn and Dn, hint, hint, such that f of Cn is equal to Sn, f of Dn is equal to Tn. Now we know that Cn and Dn are in AB. That means the sequences Cn and Dn are bounded. So now we can apply Bolzano-Weierstrass again. Since they're bounded, that means they have subsequences that are convergent, right? So C sub Pn converges to some number C, D sub Qn converges to some number D, and note that since f of Cn converges to S, all of its subsequences also converge to the same number S. That means f of C sub Pn converges to S, and f of D sub Qn converges to T. But we know f is continuous, and so by our connection between limits of functions and limits of sequences, we know that C of Pn converges to, if C of sub Pn converges to C, we have f of C sub Pn converging to f of C. Similarly, f of d sub qn converges to f of d, and it follows that f of c is the infimum, f of d is the supremum. That means, and we know that S is a lower bound for the range and T is an upper bound for the range, and that means that everything in the range has to be bigger than or equal to f of c, since it's a lower bound, and less than or equal to f of d, since it's an upper bound. And that's our theorem, the end of our proof. So our next theorem is going to be the intermediate value theorem, which may sound familiar from Calc 1. We don't have any more activities for this video, so you can go on to that video.